There are two major algorithms for genome assembly: OLC, overlap layer consensus method, and DBG, different graph assembly method. Classically, OLC method had been widely used for Sanger sequencing data. However, the computational cost of the OLC method tend to be high when the number of read sequences become large. While DBG method is computationally effective to handle large amount of data from the high-throughput sequencer. Therefore, DBG method is more suitable for assembling short-read sequencing data. OLC method is still popular for assembling long-read sequencing data. I will not go into depth of them. Please refer to literature such as shown here. There are many assemblers currently available. All of these assemblers are designed for short-read data and use the different graph method. Among them, we will use Skissa in this lecture. It is very easy to use Skissa. Just specify input files and output file name. But do not run this command directly on the interactive node. By default, Skissa will use all available CPUs, which makes CPU usage too high. You need to prepare a job script and submit a job to the grid engine with specifying CPU and memory usage. This is the job script we use this time. Prepare the file using a text editor. Specify the number of CPUs to be used here and memory usage here. In this case, the number of requested CPU cores is 5. The total amount of requested memory is 40 GB. To run Skissa, do not forget to specify the number of CPU cores and memory usage, like this. When the file is prepared, submit a job using a qsub command. You can check the job status using qstat command. It takes a few minutes to finish assembly. While waiting for that, let me explain several times. FASTA format is a standard format to describe nucleotide and peptide sequence data. The example shown above is a nucleotide sequence, and shown below is peptide sequences. A FASTA format file can contain more than one sequence data, which is often called multi-FASTA. Next, I will explain N50, which is a metric to evaluate the contiguity of the assembly. N50 is defined as the minimum sequence length that covers 50% of the total size. In this example A, when the contigs are sorted by length, the contig with length 30 kilobase pair corresponds to 50% of the total size. So N50 is 30 kilobase pair. While in example B, N50 is 3 kilobase pair. The assembly B is more fragmented than A. So when A and B are compared, A is better. Of course, N50 only evaluates the length of contigs and does not consider correctness of the assembly. There might be misassembly which can wrongly increase N50. But in general, the better assembly has a higher N50 value. Okay, the job seems to have been completed. Let's check the job results. These 4 files are log files for the job. but 3 of them are empty. So let's check this one using less command. Now you can see details of the job. If the job failed, you can inspect the log files carefully to find out the cause of the error. Next, let's see the assembly result. The file name is autoskissa.fasta. As I already said, the assembly is in a FASTA format, like this. Okay, so let's see statistics using scikit command. By specifying A option, scikit will report more detailed statistics, including N50. The total number of contigs is 61, and total length is about 2.34 megabase pair, and N50 value is 84 kilobase pair. It is difficult to tell this assembly is good or not from this N50 value alone. But N50 is useful to compare two draft genome assemblies. In my experience, the total number of contigs less than 100 is good for this size of bacterial genome. You can remove short contigs using scikit, but I will skip this part in this lecture.